Good morning students, my name is Bhanu Prakash. Today we are going to discuss a topic in chemistry called as basic concepts of chemistry. This topic is also known as stoichiometry. Stoichiometry literally means combination of three words: stoi, chio and metry. Metry means measurement. Stoi and chio represent atoms and molecules. So, the literal meaning of stoichiometry is measurement of atoms and molecules. Indirectly, this topic covers all types of numerical problems related to chemistry. We can divide this topic stoichiometry into few concepts and can be discussed separately. The first concept is called mole concept. Under this heading, we will see what is meant by mole and calculations related to moles. Mole is just like a dozen. Dozen indicates 12 units, which can be applied to anything in our day-to-day life. Similarly, in the calculations related to chemistry, this term mole is also used. Mole is equal to Avogadro number of chemical species. Avogadro number value is 6.023 into 10 power 23 units. So, quantity of matter that contains so many number of structural units is taken as 1 mole. Here structural units means they can be either atoms or molecules or ions. So, in order to measure them, we can make use of the concept of mole. Number of moles are indicated with the letter N and they are calculated as weight by gram atomic weight in case of elements, and in case of compounds it is calculated as weight by gram molecular weight. The gram atomic weights of elements can be obtained from standard scientific tables. The sum of individual atomic weights present in a molecule will give you gram molecular weight. So, by using these relations we can find out number of moles. Once we find out the number of moles, they can be converted into number of structural units or into weight or into volume. We use the term molar mass. Molar mass is mass of 1 mole of any substance. Molar mass refers to the mass of 1 mole of the matter. The matter can be either in the form of elemental state or in the form of compound state. In case of elements, molar mass will be equal to gram atomic weight. Gram atomic weight is sometimes referred to as gram atom also. Whereas, if the matter is present in compound state, then molar mass will be equal to gram molecular weight. Sometimes gram molecule is also used to indicate the same thing. Now, how to convert number of moles into weights or number of moles into number of particles and volume. 1 mole of any substance if you take, its weight will be equal to its gram atomic weight or gram molecular weight, and it is also equal to Avogadro number of structural units. In case of elements, structural units will be atoms. Therefore, if you take 1 mole of an element, it is equal to gram atomic weight and it is also equal to Avogadro number of atoms. Similarly, if you take 1 mole of a compound, its weight will be equal to its gram molecular weight and it is also equal to Avogadro number of molecules. Similarly, to convert moles into volume, we make use of a term called as GMV, meaning gram molar volume. So, this is applicable in particular for gases. In case of gases, 1 mole of any gas at STP occupies a volume of 22.4 liters. This volume is taken as a gram molar volume. Therefore, 1 mole of a gas if you take under STP conditions, then volume occupied will be equal to 22.4 liters. STP stands for standard temperature and pressure. Standard temperature is 0 degree centigrade, standard pressure is 1 atmospheres. While solving the problems, if the conditions are not under STP conditions, then we can make use of equation of state to convert, that is P1 V1 by T1 is equal to P2 V2 by T2. One set of conditions can be taken for STP and one set of values for given conditions. So, now based on this concept, how to solve few problems, let us see. For example, calculate the number of moles of glucose present in 540 grams. When a problem comes like this, we have to check what type of substance is given. Glucose comes under the category of compound with the molecular formula C6H12O6. So, for compounds, number of moles are calculated by using the relation weight by gram molecular weight. Weight of glucose is given as 540. Gram molecular weight we have to calculate from the molecular formula. Glucose molecular weight is 6 into 12, where 12 is gram atomic weight of carbon. Hydrogen gram atomic weight is 1, oxygen atomic weight is 16. So, the total comes out to 180. So, in place of gram molecular weight, we can take 180 and that comes out to 3. That means, number of moles of glucose present in 540 grams is equal to 3. As moles is a number, it does not carry any unit. Suppose a problem comes like this. What is the weight of 0.1 moles of sodium carbonate? In this problem, number of moles are given and he is asking you to calculate what is the weight of substance. Here the substance in consideration is sodium carbonate, which comes under compound category and carries a molecular formula Na2CO3. Its gram molecular weight is to be calculated first. The total comes out to 106. As it is a compound, number of moles are calculated by using the relation weight by gram molecular weight. As number of moles are given as 0.1, weight you have to calculate, gram molecular weight is 106. So, from that weight comes out to 10.6. The weight carries units and in CGS system it is grams. So, the weight of 0.1 moles of sodium carbonate is equal to 10.6 grams. Calculate the number of molecules present in 1.12 into 10 power minus 7 cc of a gas at STP conditions. So, here volume of the gas is given, we have to convert that volume into number of molecules. So, here also you have to make use of the concept of moles only. If you take 1 mole of any gas under STP conditions, it will consist of Avogadro number of molecules, that is 6.023 into 10 power 23, and it will occupy a volume of 22,400 cc, or in terms of liters 22.4 liters. In the given problem, volume is given in terms of cubic centimeters. Therefore, we are taking gram molar volume in terms of cubic centimeters. Now, reverse calculation has to be done. 22,400 cc of a gas will consist of 6.023 into 10 power 23 molecules. So, 1.12 into 10 power minus 7 cc of gas consists of how many molecules? That comes out like this: 6.023 into 10 power 23 into 1.12 into 10 power minus 7 by 22,400. This has to be simplified. 6.023 into 1.12 by 22,400 can be written as 224 into 10 power 2 into, here 10 powers will come out to 23 minus 7, that is 16. So, approximately the value comes out to 3.01 into, this comes out to 10 power 4 and that is 10 power 12. So, the number of molecules present in the given volume of gas is equal to, we can say 3.01 into 10 power 12. As number of molecules means a number, it does not carry any units here. Say a problem comes like this: what volume of hydrogen at STP is required to reduce 0.795 grams of copper oxide to give copper and water? This problem is also based on mole concept only. The difference is you have to write down the corresponding equation to solve the problem. Data will be available in the problem for writing the balanced equation. Here, hydrogen required to reduce a given weight of copper oxide to give copper and water, means copper oxide and hydrogen will be the reactants, copper and water will be the products. So, equation you can write like this: copper oxide is CuO and it is heated with hydrogen gas, will be converted into copper and water. So, it is a balanced equation, you need not balance it further. As per the balanced equation, 1 mole of copper oxide will be reduced by 1 mole of hydrogen, then we will get 1 mole of copper and 1 mole of water. Now, pick up the molar relation required to solve the problem. A given weight of copper oxide is given, you have to calculate volume of hydrogen. So, this is the molar relation required. As per the balanced equation, 1 mole of copper oxide requires 1 mole of hydrogen gas for its complete reduction. Now, these moles are to be converted into grams because copper oxide is given in terms of weight. 1 mole of copper oxide's weight means we have to take the gram molecular weight of copper oxide. Copper atomic weight is 63.5, oxygen is 16. So, the total comes out to 79.5 grams. So, 79.5 grams of copper oxide. 1 mole of hydrogen means in terms of volume, it is 22.4 liters. So, the molar relation is for the reduction of 79.5 grams of copper oxide, 22.4 liters of hydrogen gas is required. So, in order to reduce 0.795 grams of copper oxide, how much of hydrogen gas is required? That is the problem. Now, we can solve it very easily. 0.795 into 22.4 by 79.5. So, this can be simplified as 79.5 into 10 power minus 2 into 22.4 by 79.5, that comes out to 0.224 liters. or you can convert it into milliliters and represent it as 224 ml. Now see this problem. Calculate the volume of oxygen at STP required for the complete combustion of 100 ml of acetylene. So here the balanced equation required is combustion of acetylene. Acetylene's molecular formula is C2H2. Combustion means complete and rapid oxidation, means reaction with oxygen. And during combustion of a hydrocarbon, you will get carbon dioxide and water vapor along with the liberation of energy as the products. Now, first you have to balance this equation. Number of oxygen atoms on the product side are 5. So, I can write here 5 by 2 O2. From the balanced equation, now we can solve the problem. The molar relations involved are 1 mole of acetylene requires 2.5 moles of oxygen. Now, these moles are to be converted into what? For that, we have to check the problem. In the given problem, the reactants are given in terms of volume. So, we need to convert this molar relation into volume relation. 1 mole of any gas at STP will occupy 22.4 liters. Therefore, 22.4 liters of acetylene gas requires 2.5 into 22.4 liters of oxygen. Now, in the given problem, volume of acetylene given is 100 ml. So, for that how much of oxygen is required? In this way we can calculate 100 into 2.5 into 22.4 by 22.4. So, that comes out to 250 ml. So, for the complete combustion of 100 ml of acetylene, volume of oxygen at STP required will be 250 ml. How much minimum volume of carbon monoxide at STP is required to react completely with 0.112 liters of oxygen at 1.5 atmospheric pressure and 127 degrees centigrade to give carbon dioxide? Now, in this problem, the equation required is reaction between carbon monoxide and oxygen. When carbon monoxide reacts with oxygen, the products obtained are carbon dioxide. Now, you have to balance the equation first. 2CO plus O2 gives 2CO2 will be the balanced equation. In this, what we have to calculate is volume of oxygen is given and you need to calculate volume of carbon monoxide that can react with it. However, the volume of oxygen is not at STP conditions. So, first we need to convert that volume into STP conditions. For that, you can make use of this relation called as equation of state. P1 V1 by T1 is equal to P2 V2 by T2. One set of values can be taken for STP conditions, second set of values for given conditions. The standard pressure in atmospheres is 1 atm, volume you need to calculate, temperature is 273 and the given pressure is 1.5 atmospheres, volume is 0.112 liters, temperature is 127 degrees centigrade. It has to be converted into Kelvin scale. To convert degree centigrade into Kelvin scale, you need to add 273. So, that comes out to 400. From this, volume of oxygen comes out to 273 into 1.5 into 0.112 by 400. This has to be taken as a volume of oxygen. Now, coming to the molar relation, 2 moles of carbon monoxide can react with 1 mole of oxygen to give 2 moles of carbon dioxide. As the calculations involved volumes, these number of moles are to be converted into volumes itself. 2 moles of carbon monoxide volume will be equal to 2 into 22.4 liters and 1 mole of oxygen's volume will be 22.4 liters. Now, the volume of oxygen involved in the problem is equal to this much. So, it can interact with how much of carbon monoxide, that is the problem. So, in the reverse calculation way, you have to do it. The value approximately comes out to 230 ml. Calculate the amount of 90% sulfuric acid required for the preparation of 420 kilograms of HCl. Now, how can you prepare HCl starting from sulfuric acid? You should know the reaction involved. Common salt, which is represented as NaCl, reacts with sulfuric acid to give sodium sulfate and hydrochloric acid. Now, you have to balance the equation. In order to balance, you have to multiply with 2 sodium chloride and HCl2, then it is the balanced equation. Now, pick up the molar relation required. From the balanced equation, 1 mole of sulfuric acid can produce 2 moles of HCl, that is the molar relation. Now, convert this molar relation to solve the problem. The data required is in the terms of kilograms. So, we need to convert the number of moles into weights. 1 mole of sulfuric acid's weight will be equal to its gram molecular weight, which is equal to 98 grams. 2 moles of HCl's weight means 2 into 1 mole of HCl's weight. Weight of HCl is 36.5. That means 98 grams of sulfuric acid is required for the preparation of so many grams of HCl. Now, we need to prepare 420 kg of HCl. For that purpose, how much of sulfuric acid is required? So, in this way we can calculate 98 into 420 by 2 into 36.5 kilograms. But this is true if sulfuric acid taken is 100% pure. When percentage of purity is not equal to 100, the value which we have obtained from the molar relation has to be modified a little bit. And the relation we make use is 100 into obtained value by given percentage of purity. That means 100 into the value obtained is this much and percentage of purity is 90. On solving this, we get the value of sulfuric acid in terms of kilograms. It comes out to 628 kilograms approximately. What volume of carbon dioxide is obtained by heating 4 grams of calcium carbonate? So, here we should know the reaction involved. When calcium carbonate is heated, it will decompose to give calcium oxide and carbon dioxide. The equation can be represented like this. Calcium carbonate on heating produces calcium oxide and carbon dioxide. It is a balanced equation as it is. Now, you have to pick up the molar relation required. You need to calculate volume of carbon dioxide from a given weight of calcium carbonate. So, this molar relation we have to make use. 1 mole of calcium carbonate can produce 1 mole of carbon dioxide. Now, these moles are to be converted into weight because calcium carbonate weight is given. These moles are to be converted into volumes because we have to calculate volume of carbon dioxide. 1 mole of calcium carbonate's weight will be equal to its gram molecular weight, which is equal to 100 grams, and 1 mole of carbon dioxide's volume will be 22.4 liters at STP. Now, the weight of limestone or calcium carbonate given is 4 grams. From that, how much of carbon dioxide we can prepare? The calculation is like this: 4 into 22.4 by 100. So, that comes out to 89.6 by 100 or 0.896 liters, or better you represent it in terms of milliliters, that is 896 ml. 50 grams of a sample of sulfur was burnt in air. 4% of the sample was left over. Calculate the volume of air required at STP containing 21% of oxygen by volume. Like this, a problem is given. Here, the reaction involved is when sulfur is burnt in air, it will react with the oxygen to give sulfur dioxide. So, the balanced equation related to this problem is S plus O2 gives SO2. Now, what we need to calculate is weight of sulfur and amount of oxygen. So, molar relation has to be taken in between sulfur and oxygen. 1 mole of sulfur can react with 1 mole of oxygen. 1 mole of sulfur can react with 1 mole of oxygen. Now, 1 mole of sulfur means in terms of weight 32 grams, and volume of oxygen for 1 mole is 22.4 liters. Now, in the given problem, 50 grams of sulfur he says, and out of which 4% of the sample is left out, means so many grams of sulfur has not reacted. Out of 50 grams, 4% means it comes out to 2 grams. So, weight of sulfur participated in the reaction is 48 grams. Now, for the reaction of 48 grams of sulfur, how much of oxygen is required? That has to be calculated first. So, it comes out to 48 into 22.4 by 32 liters. But what we need to calculate is the volume of air required for the combustion of the sulfur in the given problem. Now, data is also given that air consists of 21% oxygen by volume. What does it mean? If we take 100 liters of air, it consists of 21 liters of oxygen. So, in order to get 48 into 22.4 by 32 liters of oxygen, how much of air has to be taken? So, that calculation can be done like this: 100 into 48 into 22.4 by 32 into 21. That comes out to 160 liters. So, those are some of the models based on the concept of mole. Now, moving on further, the next concept in this stoichiometry or basic concepts of chemistry is calculation of oxidation states. What is meant by oxidation state? During the formation of a compound, an element combines with a specific number of other atoms of an element. The combining capacity of an element with other elements is commonly called as valency, and valency, if represented along with charge, that can be taken as a oxidation state. So, oxidation state can be taken as equal to plus or minus valence. Plus is taken when the element concerned is electropositive in nature, minus if the element concerned is electronegative in nature. Electropositive elements are elements with a lower electronegativity value. They lose electrons during the formation of a compound. Hence, they get positive oxidation state value. Whereas the elements with a lower electropositivity value or higher electronegativity value, they gain electrons during the formation of a compound. Hence, their oxidation state is represented with a negative sign. These oxidation state values are calculated by following some rules. They are: the oxidation state of fluorine is always taken as -1. It is a fixed quantity. It is taken so as fluorine is the most electronegative element. Then the second condition follow is oxidation state of hydrogen. If hydrogen is in combination with the non-metals, its oxidation state is taken as +1. Same hydrogen, if it is in combination with metals, it is taken as -1. Then coming to oxygen, its common oxidation state is -2. But if oxygen is involved in the formation of peroxides, the value is taken as -1. If it is in combination with fluorine in monofluorides, the value is taken as +1, and in difluorides, the value is taken as +2. And if oxygen is involved in the formation of superoxides, its value is taken as -1/2. These are the various oxidation states exhibited by oxygen. So, as per the case, we will make use of suitable values for the calculation of oxidation states. Then, the oxidation state of any first year group element is always taken as +1, and that of second year group elements is always taken as +2. These are some of the standard values. By making use of these values, we will calculate the oxidation states of all other elements. While calculating, some other rules which are to be followed are: the algebraic sum of oxidation states of all the atoms in a molecule is equal to 0. In case of ions, the algebraic sum of oxidation states of all the atoms has to be taken as equal to the charge. If it is cation, it will be equal to positive charge, and if it is anion, it is equal to the negative charge. And oxidation state of any atom in its elemental form will be taken as 0. Elemental form means the way in which it is available in nature. Say for example, sulfur is available in nature as S8. So, if question comes like this, what is the oxidation state of sulfur in S8? You should say the answer is 0. Similarly, oxygen is available in nature in two forms, O2 and O3. O2 is called as dioxygen, O3 is called as ozone. So, in O2 as well as O3, oxidation state of oxygen has to be taken as equal to 0. So, that is what we call elemental form. And the most important rule that has to be kept in mind is the maximum oxidation state possible for any element will be equal to its group number, which is represented like this. And minimum oxidation state possible for any element is minus of 8 minus G. The maximum oxidation state possible for any element is of course plus 8. It is shown by only two elements, one is ruthenium and another one is osmium, that too in their tetroxides only. So, if for any element the calculated oxidation state value is exceeding plus 8 means somewhere the calculation is wrong. So, in such cases you can make use of this rule, and maximum oxidation state can be safely taken as equal to plus G, where G is group number of the element. Now, by making use of this concept, we have to calculate oxidation states of some of the elements in their compounds. What is the oxidation state of chromium in the following compounds? Few examples are given. Now, in order to calculate the oxidation state of chromium in chromium oxide, we will proceed like this. There are two chromium atoms. We need to calculate the oxidation state of chromium. So, let us say oxidation state of chromium is X, and the oxidation state of common oxidation state of oxygen is minus 2, and sum of the oxidation states of all the elements in a compound will be equal to 0. So, from this X value comes out to plus 3, which is the oxidation state of chromium in this compound Cr2O3. Now, coming to the second case, it is known as chromic sulfate. In chromic sulfate also we can proceed in the same manner. Chromium oxidation state you need to calculate, let us say 2x plus 3 into each sulfate ion carries a charge of minus 2 units. The net value is 0. From this X value comes out to again plus 3, which will be oxidation state of chromium in that compound chromic sulfate. This compound is known as chromium peroxide. If we calculate the oxidation state by normal method, it comes out to plus 10, but plus 10 is not a allowed value, permitted value, because maximum oxidation state possible is plus 8, and that is applicable only for two elements, that is ruthenium and osmium. Now, what is the mistake that we have committed here? In chromium peroxide, the structure, if you look at its structure, is known as a butterfly structure. Looks like this. In this oxygen link is called as peroxy bond. So, two such peroxy bonds are present in this compound chromium peroxide. So, the oxidation state for oxygen atoms involved in peroxy bond has to be taken as equal to minus 1. Only this oxygen is connected with chromium in a normal manner. So, its oxidation state value has to be minus 2. So, the sum of negative charges is minus 6, and chromium will carry the equivalent but opposite charge, that is plus 6. So, whenever you get abnormal oxidation state values during the calculation, we have to check for structure. When you are not sure of the structure, you can apply the rule maximum oxidation state possible for an element is always equal to its group number. Chromium, as you know, belongs to D block, and it is present in 6B group. So, its oxidation state value can be safely taken as equal to plus 6, which will be true even from the structure. Then coming to the next case, this compound CrOH thrice is called as chromium hydroxide. In this, If X is taken as oxidation state of chromium, each hydroxide ion will carry 1 unit of negative charge. Net value has to be taken as equal to 0, and from that the oxidation state of chromium comes out to +3. In this manner, for any element in any compound or ion, we can calculate the oxidation state values simply by applying the rules. Whenever you get abnormal values, check for the structure of the compound, or better you apply the relation that maximum oxidation state is equal to plus G and minimum oxidation state is equal to minus of 8 minus G, or you can convert it as G minus 8. In that way, oxidation state of any element can be calculated. Balancing of redox equations by ion electron method. A redox reaction means the chemical reaction in which both oxidation and reduction take place. Oxidation involves loss of electrons, reduction involves gain of electrons. The method is known as ion electron method. It is also called as half reaction method. Now, to balance the equations by this method, following rules are to be followed. First rule is we have to divide the given equation into two half reactions, namely oxidation half reaction and reduction half reaction based on difference in the oxidation state values. After dividing the given equation into two half reactions, each half reaction has to be balanced in the following sequential order. First, we have to balance elements other than oxygen and hydrogen by trial and error method. That means just we have to multiply with suitable numbers so that the element is balanced. Then we have to balance oxygen, and the rule for balancing of oxygen is add required number of water molecules on the deficient site. Then you have to balance hydrogen. For balancing of hydrogen, we have to check the medium of the reaction. If the reaction takes place in acidic medium, on the deficient side, straight away we can add required number of H plus ions. If the reaction takes place in basic medium, first we should add water molecules on the deficient site and equal number of OH minus ions on the opposite side. Then finally, charge has to be balanced by means of addition of electrons or subtraction of electrons. In the final stage, again the two half reactions are added together to get completely balanced equation. So, these are the rules to be followed for balancing of redox equation by this method known as ion electron method, also called as half reaction method. Now, we will take up two examples and see how to balance those equations by means of this method. Now, we have to balance this equation by ion electron method. When a reaction is given, we should check above the arrow mark. If H plus ion is present, that indicates reaction is taking place in acidic medium. If here OH minus ion is present, it indicates that reaction is taking place in basic medium. The first step that we have to do is calculate the oxidation states of elements other than oxygen and hydrogen. Here in the given problem, other than oxygen and hydrogen, the elements present are manganese and sulfur. Here the oxidation state of manganese will be +7, sulfur +4. In the product side, manganese oxidation state is +2 and sulfur oxidation state is +6. So, for manganese there is a decrease in oxidation state from +7 to +2. Wherever there is a decrease in oxidation state, that should be taken as a reduction half reaction. Then for sulfur, oxidation state is changing from +4 to +6. When there is increase in oxidation state, that should be taken as a oxidation half reaction, commonly represented as a OHR. Now, in this way, we have divided the given equation into two half reactions, namely reduction half reaction and oxidation half reaction. Now, we have to balance each half reaction in a separate manner. First, let us separate the reactions. The order of balancing of equations is element other than oxygen and hydrogen, oxygen, hydrogen and finally charge. This can be used in the form of a checklist. Now, in this half reaction, element other than oxygen and hydrogen present is manganese, which is already in a balanced state. Then coming to oxygen, on the reactant side there are 4 oxygen atoms, on the product side there are no oxygen atoms. So, as per the rule, on the deficient side we have to add required number of water molecules to balance oxygen. As there are 4 oxygens, here we are adding 4 water molecules. With that, oxygen is balanced. Then coming to balancing of hydrogens, on the product side there are 8 hydrogens, no hydrogens on the reactant side, and reaction is taking place in acidic medium. Therefore, as per the rule, on the deficient side, that is reactant side, we will add required number of H plus ions, that is 8 for balancing of hydrogen. Finally, we have to balance charge by means of electrons. For that purpose, the difference in oxidation state has to be taken. Initial oxidation state is +7, final oxidation state is +2. The difference is 5, and as it is reduction, it involves gain of electrons. Therefore, the difference in oxidation state is taken as number of electrons on the reactant side. With this, we have balanced the charge. Now, same procedure has to be applied on the other half reaction also. Here, the element other than oxygen and hydrogen present is sulfur. It is also in a balanced state, so you need not balance it. Next, oxygen. On reactant side, there are 2 oxygens. On the product side, 4 oxygens. As per the rule, the oxygen atoms are balanced by adding required number of water molecules. In this case, it is 2 water molecules. Then, for balancing of hydrogen, on reactant side there are 4 hydrogens, whereas on the product side only 1 hydrogen, and the reaction is taking place in acidic medium. So, on the deficient side, we can add required number of H plus ions. SO2 plus 2H2O gives HSO4 minus plus 3H plus. With this, hydrogen is balanced. Then coming to balancing of charge, sulfur oxidation state is changing from +4 to +6. So, difference is 2 and it is oxidation. As oxidation involves loss of electrons, it is depicted on the product side. So, the last stage is Now, the two half reactions are to be added to get completely balanced equation. For that purpose, before adding, we should see that number of electrons in either of the reactions are same. If they are not same, multiply with suitable numbers. In this case, number of electrons are not same, so we will multiply this equation with 2, this equation with 5, and then we will add the equation. Multiplying this equation with 2, we get 2MnO4 minus plus 16H plus 10 electrons gives 2Mn plus 2 ions plus 8H2 water molecules. Multiplying the second equation with 5, we get 5SO2 plus 10H2O gives 5HSO4 minus plus 15H plus 10 electrons. While adding the two half reactions, if anything are common on opposite sides, they can be subtracted. Here the number of electrons are equal in number, they get cancelled. 2MnO4 minus plus 5SO2 plus, here 10 water molecules, on product side 8 water molecules are present. So, the difference can be taken as 2H2O. Here 16H plus ions are present, on the opposite side 15H plus ions are present. The difference will be 1H plus ion. On the product side, you will get 2Mn plus 2 plus 5HSO4 minus. So, this is the completely balanced equation which can be verified in this order: element, oxygen, hydrogen. As far as elements are concerned, 2 manganese atoms are present on the reactant side, 2 on the product side. Sulfur, 5 sulfurs, 5 sulfur atoms on the product side. That means element is balanced. Checking for oxygen, on the reactant side 8 plus 10, 18 plus 2, 20 oxygen atoms are present. On the product side also 20 oxygen atoms are present. That means oxygen is balanced. Last, we have to check for hydrogen. Here 4 plus 1, 5 hydrogens. Product side also 5 hydrogens are present. That means the equation is completely balanced. In this way, we can cross verify whether the equation is completely balanced or not. So, this is about balancing of redox equations by ion electron method when the reaction is taking place in acidic medium.